Modern organizations collect a staggering volume of data, yet most of these millions of individual points offer very little actionable clarity. To find meaning, analysts typically rely on traditional, linear statistics. These models operate on the assumption of simple one-to-one cause and effect relationships, expecting that if variable A moves, variable B will follow a predictable, straight path. But the systems we study are rarely that simple. Reality exists as a tangled, interconnected web where dozens of variables push, pull, and influence each other at the same time. Relying on these straight-line mathematical models in a multidimensional world leads to a dead end. The math simply cannot account for the complexity of the actual environment. Beyond the raw volume of observable data lies a more complex obstacle: forces we know exist but cannot directly measure. In statistics, these are known as latent variables. These are abstract concepts. You cannot put a ruler to customer satisfaction in a retail study or directly measure patient resilience in a clinical trial, yet their presence is undeniable. Here, that central void is the latent variable. Though invisible, it exerts a constant distorting pull on surrounding measurable data points. When standard equations ignore these hidden forces, their rigid connections snap under the pressure, leading to false conclusions. Meaningful analysis requires more than a higher volume of numbers. It requires a structural method to map the influence of these invisible forces. This structural method is known as structural equation modeling, or SEM. SEM is a statistical framework specifically designed to map multivariable relationships. Its primary function is testing theoretical models that combine the hard data we can see with the latent variables we cannot. However, executing SEM manually is an exhausting process. Calculating how one hidden variable impacts an entire ecosystem requires solving layers of simultaneous, intersecting equations. It is a level of mathematical labor that most researchers cannot sustain. This friction keeps these insights out of reach for anyone without a PhD in advanced mathematics, effectively locking the door on vital structural data. SEM provides the necessary logic for modern research, but it remains a specialized manual process that requires a technological bridge to be practical. That bridge is AMOS, which stands for Analysis of Moment Structures. It is the software solution designed to automate the heavy lifting of SEM. AMOS functions as a translation engine. It takes those dense statistical equations and converts them into a visual workspace. In this interface, researchers use a path diagram. Instead of writing out formulas, they place circular nodes, each representing a variable, directly onto a digital canvas. By drawing directional arrows between these nodes, the analyst can establish the flow of influence and the specific relationships within the model. While the user works, AMOS calculates the statistical weight of every connection in real time. Notice how the lines thicken or thin based on the strength of the influence. The analyst is no longer staring at a chaotic spreadsheet of isolated numbers. They are interacting with a coherent structural map. By translating raw data into a spatial environment, AMOS maps the architecture hidden inside data chaos. This visual mapping changes how major industries navigate their most complex problems. In healthcare, researchers use AMOS to see how patient demographics and hidden health indicators alter the success of a treatment, leading to more accurate clinical strategies. In the social sciences, sociologists use it to trace the precise pathways through which social media usage impacts the mental health of a community. Marketers use these diagrams to find the latent drivers of loyalty. This chart shows a latent brand trust node influencing pricing and advertising before converging on a final purchase decision. By using these models, organizations move away from guessing and begin to prove the structural realities of their systems. As we look toward the future of data-driven research, the landscape is only becoming more crowded. With the global volume of information continuing to rise, tools like AMOS are becoming a necessity for anyone trying to maintain a strategic edge. Simply hoarding more data is no longer enough. The advantage goes to those who can extract structural clarity from the data they already have. The ability to map invisible connections and turn chaos into insight is what separates noise from true understanding.